Okay, so this was what we had done last week. Well, we basically finished our discussion on the Grassmannian path integrals, and we discussed the Wick theorem that we could also use the Grassmannian path integral to drive the perturbative expansion. And then we looked at what do we do with gauge fixing. Now, when we write the path integral in this form in terms of summing over all configurations of the vector field, vector potential, now basically for the physical system is described by the electric and magnetic fields, not by the vector potential. But for a given electric and magnetic field, there are infinitely many vector potentials. So here, in this way, we are not summing over only the physical configuration, but we are double counting, infinitely many counting in fact. So that was one thing we were looking for. How can we fix that? And let me just go to the result we had. We had shown this identity. Now, what is this? On the left, we have a path integral over all configurations of the vector potential. So we are essentially multiply counting. For a given physical state, we have many contributions to that path integral. On the right, just look at this term. This determinant and this Dirac delta makes sure that this G function is kind of arbitrary, but those two make sure that we are counting just one vector field configuration corresponding to each physical state. So in a sense, you can think of it like this. We need to sum over physical states. But for each physical states, we can describe it in terms of 5 different ways. And rather than choosing one of those 5 different ways and sum over all of them, we can sum over all possible descriptions. Of course, we are multiply counting. We are counting every physical state by 5. But that's not a problem. We can just divide the result by 5. So here, this path integral here sums over all the physical configurations, let's say. There's no overcounting over there. That Dirac delta makes sure that we only choose one A mu that describes our physical state, but at the same time, it satisfies our gauge fixing condition. And the relation between those two is just a number. Well, this determinant is actually inside this second path integral. So we are just summing over this alpha. So basically, what this tells us is, well, you can just sum over all A mu's, all vector potentials. Forget about gauge fixing. And which is not, strictly speaking, not the correct way to proceed. What we should do is, among all the A mu's, we should choose a single one corresponding to a given electric and magnetic field. But this equality tells me that forget about that, just sum over all A mu's. The overcounting will be just given by this factor. So just divide by that factor and you get the sum over all the physical states. Or every physical state is counted by just 1. But that's just a normalization of my path integral. And at the end of the day, I'm just summing, I will be taking ratios of path integrals. So I don't really care about gauge fixing at this stage, let's say. Even if I don't fix the gauge over all these A mu fields, I get the same result. But still there is a problem. Let's say one of you were asking, okay, why did we introduce omega and then nothing depends on omega? We will introduce it in a moment. Now there's still a problem. Okay, this tells me that I can ignore the gauge fixing condition Dirac delta over here, sum over all possible gauges. But I cannot work with this thing because I know how to work with Gaussian integrals. I know how to do perturbative expansion, etc. Here there's a Dirac delta which I don't know how to work with. On the other hand, I also cannot work with the left-hand side, because if you remember how we deal with path integrals, we just convert them to a Gaussian integral, and then the path integral just becomes 1 over the square root of the Dirac delta, 1 over the determinant of that operator, of that Gaussian. But the Gaussians we have has 0 determinant. If you remember in 541, we had seen that we couldn't invert the equation of motion vector for the vector field because there's a 0 eigenvalue. So I also cannot work with the left-hand side. I cannot work with the left-hand side, I cannot work with the right-hand side. But I can modify the right-hand side and convert it to a form that will allow me to work with. So what I do is, Now, this is arbitrary in the sense that whatever gauge fixing condition you impose, this equality holds. I choose a particular gauge fixing condition. I mean, this is not strictly speaking the Lorentz gauge. Remember, Lorentz gauge is del mu a mu is equal to 0. I'm just saying that del mu a mu should be the given function. This is, let's say, my gauge fixing condition. And I already know that this integral, whatever the value is, it is independent of omega. Basically, if you look at this equality, you see this side, the left side, is independent of what function you choose as g of a. I don't care about that function. But this is also independent of whatever g is. So I have to, this integral should be independent of whatever g is, whatever gauge fixing condition I impose. So the result of this path integral should be independent of omega of x. But that means I can, again, just sum over all possible values of omega. I will be, again, overcounting. But then I just divide by, well, how many times I count, how many different omegas I sum over. So that is the basic idea over here. I'm just sum over omegas. I know that they will be all contributing the same. So I'm giving them some weight. And I'm just dividing by the total weight of omegas. So I'm essentially multiplying by 1. And that allows me to write my path integral in this form. Okay, what does this tell me? Well, here I also introduced an operator inside my path integral because essentially I will be looking at time-ordered products of operators. And all these steps I can do with this operator, assuming that my operator is invariant under this gauge transformation. So if I have any gauge invariant operator appearing here, I can write it, I have this equality. Now this n over here, this normalization, now it depends on psi. It's not independent of psi. So this integral over here, I cannot really claim that it is independent of psi because of this normalization. But at the end of the day, again, I will be basically looking at ratios. You see, these are the things that I will be interested in. And in the ratio, these normalizations basically will cancel. So what that tells me at the end of the day is if I add such a term to my Lagrangian, just add such a term. Now, what do I gain by adding that term to my Lagrangian? Well, my Lagrangian is still a Gaussian, but now the determinant that I need to evaluate is, the matrix is invertible, and it has a non-zero determinant. It doesn't have a zero eigenvalue. And so those are, all my computational methods depend on my ability to take the inverse of that matrix, and hence the determinant should be non-zero. Now I have this equality, which tells me that, oh, I have a gauge symmetry, but just add this term. And you are not changing anything. This is what this identity tells me. But adding that term, my Gaussian, the matrix appearing in my Gaussian is now invertible, I can work with it. And of course, this is valid. So this matrix element of a gauge invariant operator, I can calculate using just adding this term to my Lagrangian. But then there are problems. You see, this integral should be independent of psi. This will be independent of psi because basically I started with a definition that doesn't depend on psi. And then I always have equalities. So the final result, although psi appears in my final result, still it should be independent of psi. Now this works because this operator I introduced there is gauge invariant. But in general, I will be looking for endpoint functions. Endpoint functions are not gauge invariant, and hence their matrix elements will depend on gauge, and hence it will depend on this psi. That might lead to a problem because whatever I measure the scattering amplitudes, S matrix elements should still be gauge invariant. And S matrix elements, we already know that we can write it in terms of these endpoint functions. So on one hand, I have the endpoint functions which depend on gauge. Using these gauge-dependent endpoint functions, I can calculate the S matrix elements, which should be independent of gauge. That is something we still need to show. So any questions up to here?
I assume everything follows similarly for SE2 symmetries?
No. You see, the problem will be, you see, look at this determinant. It is independent of A. In non-abelian theories, we will study in the last month of this course, that determinant will depend on the gauge. So we cannot just take it out of the integral. We will have to do something else with that. But the basic idea will still be the same. I mean, here it was simple because I could take this determinant out of the integral and play around with what remains. In the non-abelian cases, I won't be able to take that determinant out. I need to do something else.
But in any case, I need to do something. Gauges are not physical objects.
Sure. The physically observed, gauge freedom, in Schwartz, for example, it says that gauge freedom is not a physical symmetry. In the sense that he claims that, okay, I need to have 3 degrees of freedom. But then I choose, in a sense, to describe these 3 degrees of freedom in terms of 4 degrees of freedom, the 4 vector. And hence I have these superfluous degrees of freedom, not because of the physics, but because I choose to describe my system in terms of extra degrees of freedom. Of course, that extra degrees of freedom shouldn't change my result. I could have chosen to work with 3 degrees of freedom. It becomes a hell of a computational tool. But that is equivalent to gauge fixing. We impose one condition on these 4 degrees of freedom so that the independent degrees of freedom is still down to 3, and in fact 2.
It won't be independent of A because the way, I remember the way
nonlinear, yeah. The gauge transformations will not be as simple as this one. That is why things will be different. So any other questions about this simple case? Now, we also didn't discuss the conservation laws yet in terms of this path integral formalism. Somehow we should be able to derive our conservation laws.
Out of this context, I understand what you mean by all of this degrees of freedom and stuff. But is there any kind of approach that these gauges somehow has a deeper meaning in our reality? So they might indicate something physical or something.
Well, you see, things get complicated when you also consider, let's say, the Bohr-Aronov effect. We always say, okay, the physical degrees of freedom are the electric and magnetic fields, but then you just take a solenoid. There is a magnetic field only inside the solenoid and no magnetic field outside. And you put a shell, infinitely high shell, inside the solenoid so that the electron cannot even penetrate, the wave function cannot even penetrate into the shell. But still, the electron feels the magnetic field in the Bohr-Aronov effect. Well, strangely enough, the effect still turns out to be proportional to the magnetic field inside the shell. So there are all these discussions about whether the vector potential is actually real or not. Is it actually physical or not? I don't know all the details, to be honest, of that discussion. It's not a trivial question to answer, in the sense that the electron never, if the electron never enters a region where the magnetic field is non-zero, still it feels the effect of the magnetic field due to the vector potential. But the effect that you observe is still proportional to the magnetic field, not the vector potential. So let's look at global symmetries. and what they will tell us. Let's look at QED. We know we have path integrals of this form. And if you want to have, let's say, any fields, let's look at such a matrix element. Now I know that QED is invariant under this transformation. Let me introduce Q1 here. Now I'm basically entertaining the idea that I might have more than one psi fields, if you like. And each of these psi fields, they will have different, they might correspond to particles with different electric charges. So under a U1, they don't get all the same phase, e to power I alpha psi 1, but the phase that they acquire will depend on their charge. But still, my theory is invariant under this gauge transformation, and this matrix element, well, if psi and psi bar, they have the same charge, that will be invariant. If they have different charges, it won't be invariant, etc. But I won't look at this to study how my path integral changes or to obtain some properties about gauge conservation laws. What I will look for is I will make a change of variables. I will take psi go to e to power I alpha x q psi, and then psi bar goes to e to power minus I alpha x q of psi bar. I'm just taking this phase to be position dependent. I'm not looking at the gauge transformation. I'm just saying that, okay, I have this global symmetry. Let me look at what happens if I convert that global symmetry, assume that global symmetry is a local one. I know that this is not invariant. If I want to leave my Lagrangian invariant, I should keep A. I should also transform A, which I don't. Well, then what happens is LQED becomes, there's an invariant piece. Well, there will be also plus del mu alpha x j mu of x, where j mu of x will be q psi bar gamma mu psi. Well, in the simplest case of one scalar field, LQED, the relevant part for me will be psi bar I del slash minus m psi plus q a mu psi bar gamma mu psi. This part is invariant under this transformation. This part is invariant under the same transformation, but this part is not because alpha is local. So this becomes psi bar, well, let me write it down, minus I alpha x, well, let me take this minus this one plus. This is plus q I del slash e to power minus I alpha x q psi plus the other terms that do not change, and this is psi bar I del slash psi. If I act the derivative on my psi field, this is what I get. Then I have, when the derivative acts on this exponent, I will get plus del mu alpha x q psi bar gamma mu psi. So my Lagrangian changes. Now let's go back to my path integral. I'm basically writing a shorthand. This becomes under this transformation, and in the understanding that for field psi I has a charge qi, so qi replace it with qi, etc. And I get e to power I sqed. Remember, the Lagrangian of QED remains the Lagrangian of QED plus this additional term. So I get plus I d4x del mu alpha x j mu of x. It is this term. Then I have psi I of xi plus minus I alpha qi psi I I'm expanding everything up to order alpha. Well, I will also do the same thing with that exponent. I have my Bézier, I have the QED Lagrangian, QED action. Then I have 1 plus I d4x del mu alpha j mu of x times, well, let me just keep the terms that are up to linear order in alpha. Then I have minus I minus alpha sum over I alpha at the point xi qi product over I psi I product over j psi bar j plus I sum over j alpha xj qj so what if I just had two of these terms, I would have psi plus I alpha q psi times psi bar minus I alpha q1, let me call them 1. This is 2, q2 psi 2. This will be psi 1 psi 2 bar. It is this term. Then I have this times this one, which will be plus I alpha at the point x1 q1 psi 1 psi 2 bar. Then I will have this times this term, which will be minus I alpha x2 q2 psi 1 psi 2 bar, plus terms of the order of alpha squared or higher. Well, this is no, sorry, my gauge transformation, I have the minus sign in the transformation of psi, so this is minus, this is plus. Well, this is just this term over here. I just have alpha x1 q1, alpha x2 q2, etc. If I had more than two terms appearing here. This is just this term appearing over here. And of course I have terms higher order in alpha. Now last step, I have to multiply all of this thing with this one. I get this one, contribution from this one, which will be I will just rewrite it. And this is the contribution from this one. And for this one, well, I have to multiply it with this term only. This term times these terms are all alpha squared or higher. So that will give me an additional plus I d4x del mu alpha I del mu alpha x j mu of x plus, again I repeat, terms higher order in alpha squared. And keep in mind that what I'm actually trying to calculate is this thing divided by z. I will just lazy to write it down. So here I have all 1 over z. So I started by trying to calculate this one. This is what I was trying to calculate. It is my path integral, the operator inside my path integral divided by z, which is nothing but the path integral without that term. That is what I'm trying to calculate. And now what do I obtain? Well, this part is exactly the same. So I have exactly the same term. Then I have, let me take these ones, minus I, sum over I, alpha x I, q I. These are not operators. I can take them out of my path integral. What remains is again the same term. Then I have, for this one, again, I can just take the sum over these j's. What remains is again the same matrix element. Then I have this term. Okay, again, the x integral is independent of my path integral, so I can just take it out. what remains now is not the same matrix element, but now I have an extra J mu. Okay, what I did, I just started with a path integral, this path integral representation of this matrix element. Then inside that path integral, I just made a change of variables. Remember, path integral is just an infinite dimensional integral. If I make a change of variables in an integral, the value of the integral doesn't change. I'm not talking about any symmetry of my system. I'm just saying that whatever my system is, I write it as a path integral, and then I make a change of variable. Nothing should change. Then I look at, under that change of variable, I looked at how my action changes. I say that under that change of variable, my action just gets an additional piece. At least for the particular Lagrangian I'm considering. And then whatever is inside my path integral, all these terms, they also change. Because I have to express the old integrand, the old expressions inside my integral in terms of my new variables. That is why they change. Here and here. Then, okay, there's now I have my new parameters, which I use to change my integration variable. My expression looks as if it depends on that new variable. So although I just made a change of variable which depends on certain parameters, my integral shouldn't change, my result shouldn't change. It seems as if it changes. Then what I did, I just made a Taylor expansion in terms of these new variables I introduced, new parameters I introduced, not variables. And then I just looked at the linear term. And this is what I obtained, plus corrections of the order of alpha squared. So I have this expression written in terms of path integrals. I just made a change of variables in my path integral, introducing some parameters that my path integral seems to depend on those parameters. I just expanded my new expression in terms of those parameters, and this is what I obtained. But I know that this expression has to be the same as my initial expression, because just changing variables in an integral doesn't change the result of the integral. Which tells me that these terms should be zero. These three lines, those are the contributions at linear order in alpha, they should be exactly zero. And so, of course, I still need to do one more trick here. I need to do an integration by parts. If I do an integration by part, you see, there are two things I will do. Alpha xi is d4 x alpha x Dirac delta x minus xi. What this tells me is I can write these terms also as Dirac deltas, as four-dimensional integrals. And this one, I just do an integration by parts. So all those terms will be d4x alpha of x minus I del mu this is this term. Integration by part gave me this minus sign. Then I have plus I it is this term here. And then I have this last term. This should be 0. And remember, these alphas are just arbitrary variables I chose, whatever those arbitrary parameters I chose to define my change of variables. And whatever alphas I choose, this should be satisfied, which basically tells me that whatever is inside my integral should be 0.
Where is the direct alto of first term?
There's no direct alto of that term because it's already inside the d4x integral. This term is already, there's a d4x integral, there's an alpha over inside that. I just had to do an integration by part to move that derivative to the derivative of this matrix element. For the other terms, they don't have a d4x integral. I just inserted Dirac deltas in those two lines so that all these three terms can be written as a d4x integral multiplied by alpha x. Now, let me just take the case where I have just two fields. This is the general expression, but it will probably be cleaner when I just take two fields. So basically I have minus I del mu time ordered product of j mu of x psi of x1 psi bar of x2 plus I q2 Dirac delta x minus x2 psi of x1 psi bar of x2 and minus I q1 x minus x1 this is equal to 0. Or in fact, let me just rewrite it once more, get rid of the i's. This is the identity I have. So where is the conservation law? I'm looking at a system with a global symmetry. There should be a conservation law here, and yeah, this is my conservation law. Do you see it? Yeah, you see.
If you take the derivative, there will be an additional piece which will perhaps cancel all the other things. Del mu and j mu will be equal to 0.
Well, what will happen is, you see, if you would just, as your friend pointed out, take this derivative. If you try to evaluate this derivative without using any path integral, just a matrix element, this will be, okay, there will be this one. But remember, this derivative, I'm summing over all mu, there's also derivative over time appearing there. And time integral, time ordered product has step functions whose derivatives would give me Dirac delta functions. So I will have a term which will have Dirac delta of x1, x0 minus x10 times the commutator of j mu of x psi of x1 psi bar of x2. And another term which will involve x0 minus x2 0. No, these are J0s. But now here I have equal time commutation relations of charge density and the field, which will be J0 of x These are the equal time commutation relations. And hence, we recover this term. Well, these Dirac deltas are all four-dimensional Dirac deltas. Well, without knowing anything about J mu, you can put any operator there instead of J mu. And this equation this will be the equation you get. If J mu is the charge density, these commutation relationships will give you the charge times the field itself. But there is this term, which is absent here. So basically, this equation tells me that del mu J mu is equal to 0 because of the absence of that term. And hence I have the charge conservation. So this equation here is the charge conservation due to this global symmetry. Or if you like, this is the general form. Let me take this one.
Here Q's are free parameters, right?
No. No, Q, they are not free parameters. They are the charges corresponding to psi and psi bar fields. You see, here, these Qj's is the charge of the psi j field, and Qi is the charge of the particle corresponding to the psi I field. Whatever electric charge they have. They are free in the sense that the particles can have any electric charge that you can think of. They don't have to be integers. But once you have your particles, once you identify your particles, you have their charges. These Qi's and Qj's appearing in this expression are the electric charges of those particles.
It's also kind of an intuition that we derived a conserved current using local symmetry.
I didn't use local symmetry.
But did we not change the phase?
I considered a phase transformation. You see, the main idea is over here. Now let me write it here.
The saying by changing of our variables, meaning in the end we make the integral locally invariant, right? Because
my integral is not. You see, I don't even have to have a vector potential here. I didn't use it. Even if I just have this part, just a free Dirac equation. The only thing I use here is if my particle has symmetry under a local gauge under a global symmetry. Under a global symmetry, the QED Lagrangian doesn't change. So that also tells me that if I take this global symmetry local, my Lagrangian will not be invariant, but all the changes in my Lagrangian should be proportional to the derivative of this symmetry transformations. So that if alpha is independent of position, that derivative would be 0. In fact, if you remember from 541, we made argument. Using this argument, to demonstrate that the vector potential has to couple to the current. It cannot have arbitrary coupling. The gauge field, or if I would write down a field for A mu also, A mu should couple to the conserved current. I don't have any option there. So what I use is that this part of the Lagrangian does not have a local symmetry, which allowed me to drive this relationship. Because if I was looking for a local symmetry, that would tell me that a global symmetry, that would tell me that I should also change the A field, but then this SQED under that transformation wouldn't change at all. So I wouldn't get any property of the conserved current. And these are called the Ward-Takahashi identities. They will allow me to prove the gauge invariance of my theory of the S-matrix elements. But whatever fields I have here, for example, although I just wrote psi fields in those products, I could have inserted, I don't know, the vector potential in those products. I could just add A mu fields there. But since A mu fields do not change under they have zero charge, well, this equation wouldn't be modified. Just add as many A fields here, as many A fields here, if you like. It will remain the same. Or, you see, I could have added some other conserved currents. Here I could have added terms psi bar gamma mu psi. Again, they wouldn't change this relationship because psi bar gamma mu psi is invariant under the transformation that I consider. You see, I could have looked at this term. I just insert, next to psi's, I just insert an electromagnetic current density. Well, this will still be equal to this expression. Of course, now I have J nu x1 Why? Because J mu and J nu commute. I would get such commutation relationships with J0 and J nu, and it is 0. Or you can say that this operator here doesn't have a charge, it has a charge 0. So the corresponding term is multiplied by 0.
Here Q1 and Q2 correspond to charges, and we have a theory of fermions, and I would imagine that one charge would correspond to, let's say, electron, and the other one corresponds to the antiparticle of a positron, and I would assume they would have the same magnitude. Is it the case here?
Well, you see, I'm just saying that there is a single field. So this Q1 and Q2 is actually the Q of that field. I don't have two different charges. But I just wanted to make sure that this corresponds to the charge of that field and this corresponds to the charge of this field. That is why I kept them Q1 and Q2. But they are the same charge, Q1 and Q2, they are equal to each other.
Equal to each other? I mean...
Equal to each other.
With minus?
No. Equal to each other. The difference in the minus sign is already over there.
Okay.
They are equal to each other. If I had more than one kind of field, then these Qs might be different for different fields. Okay, let's have our break.
This is
Yeah.
the first order conservation, right? If the what is called anomaly is when this is not conserved.
Yeah, okay. You see, in this derivation, there are a couple of things I used. One, the Lagrangian is invariant under this global transformation. And hence, I know that the Lagrangian just changes by the derivative of this alpha. And whatever is multiplying this derivative of alpha is what I call the curve. That is one thing I used. Now, the second thing I used in going from here, this step, to this step, is I assume that this is invariant. This doesn't change. For this symmetry, it doesn't change. Because basically, at every space-time point, I will have deep psi x1, deep psi bar x1, which is d times, after the transformation, after going to the new variables, this will become e to power d e to power I alpha x1 q1 psi d e to power minus I alpha x1 q1 psi bar. And you see, at x1, they are both constants. So these will cancel each other. So for this theory, for this symmetry, there's no problem. But it turns out that there are certain changes of variables, not this one, but there are other change of variables which leave the action invariant. The action still doesn't change. But the measure of the path integral changes. So while the action doesn't change, it basically tells me that if the action doesn't change, the classical theory is invariant under this symmetry. But the quantum theory is defined by the path integral, not the action only. By the path integral. The path integral does change because the measure changes. And hence, the quantum theory doesn't have this symmetry. This is what's called the anomalies, where symmetries that have these anomalies, the measure changes, and hence the theory is not invariant, although the action is invariant. Okay, maybe towards the end of the semester we will have an example of that. Not yet.
Is there any analog of the conservation law? Actually, you said that that's the also identity, right? That the last thing we write, I mean, like continuity equation or something.
This one?
Yeah.
Well, you see, those theories, they don't have a symmetry. So there is no conservation law. You see, conservation law is this one. In those theories, then you can define a J mu. Classically, it will be conserved. But when you calculate the quantum mechanical corrections, it turns out that the divergence of that J mu, the four divergence, is non-zero. And you can also calculate them. Since the divergence is non-zero, it's no longer conserved, which basically tells us that it's not a symmetry of the quantum theory. Okay, let's have our break.